Namaste, Shubhodaya, and warm welcome to the viewers of the CSIR sponsored CSIR 4PI organized Vismaya Vigyana lecture series season 2. Just like last year, we have organized some awesome topics for the webinar for school students. Myself, Pavitra, senior scientist here at CSIR 4PI, welcome you once again for this initiative. Without much delay, tell you about what does Jigyasa stand for. Jigyasa is an initiative that is headed by Jigyasa team back in Delhi, where the main context is to connect the science with the students using our scientists of CSIR 4, sorry, not 4PL lab, just CSIR labs. I now welcome Dr. Sridevi Jare, head CSIR 4PI, to the event. Ma'am, the day is yours.
Good morning. Welcome to all the school students who are online. On behalf of CSIR 4PI, I extend a warm welcome, and on behalf of myself as the head of the institute. So you all must be thinking, what is Fourth Paradigm Institute? Basically, Fourth Paradigm Institute is related to fourth paradigm of science. So today the talk is also related to that only. So the fourth paradigm of science, that means there are three paradigms before that. For us to say define the fourth paradigm of science. So the actual science, the moment we say the two topics that come to our mind is maths and physics. Okay, maths is a standalone science, but physics is not a standalone science. So from there we start our this thing. So our first paradigm of science is observation. Like we sit and look, gaze at the stars every day, day in and day out, and say, "Oh, this star has moved this much." So that is your observation. That is the first paradigm of science. The second paradigm is when you write an equation saying how much the star has moved. So that becomes your second mathematical expressions to when I describe the observation. And then you solve that expressions analytically. That is without the use of computers, just like you school children must be doing. That is the second paradigm of science. Your third paradigm of science is when the equations become so complex that you have to use computers to solve them. So that becomes your third paradigm of science. So now the fourth paradigm of science is basically see, nowadays you have so much of, that is the topic, today's topic also, big data seismology. We have so much of data. Now the data, nowadays, earlier gold, silver was the priciest possessions, but now, data is supposed to be the most expensive possession. So, the data, what does the data tell? So that is what is big data, that is data intensive scientific discovery. So when you discover something through the data, large amount of data, and that is what is called fourth paradigm of institute. Our institute works in that research area. So under both we do domain agnostic data science for any application. It can be any application. It does not matter whether it is earth sciences or seismology, climate modeling, or for some energy, this thing, anything we will do, that is domain agnostic data science. We also have a very dedicated domain experts. Like now the one who's going to talk is a domain expert in earth sciences and seismology. So domain experts who understand the science and physics, the phenomena. See, the problem with data is you can misuse it. So, so data without science does not make any sense. That is, when you observe, see your data, like you have a particular disease. Okay, the data, like you say, you have a huge amounts of data. Then you ask the data. Like you say, right now we have Chat GPT. You ask Chat GPT how many people, and give it the data, how many people in this country with this particular symptom have diabetes. Okay, just like in during COVID time, they have did big data analytics, and they said that people who smoke cigarettes are less prone to COVID. That is the result you got from the data, but then that should be backed up by the physics and science. That is where the domain expert comes. So we simply can't say the data says that all the cigarette smokers are not prone to COVID is not okay. So you have to back it up with your science, physics knowledge. That is where the domain expertise comes. And So we have both in our institute, and today our speaker has both the expertise, both domain and the big data expertise. I welcome Dr. Anil Earnest, and I hope all of you would enjoy this lecture series spanning over 3 days, starting today. Okay, thank you. Over to you, Pavitra.
The mic is mute.
You're mute, Pavitra.
Now,
Yeah,
Yeah.
it's good.
okay. The main objective of this talk is to provide an overview of current scientific developments supported by big data seismology, as well as new trends, potential difficulties, and future prospects. The talk is planned to be streamed live through three different sessions and is structured to serve as a starting point for students or others interested in getting introduced to a variety of topics, including seismic imaging and earthquake source physics. Let's introduce or let's welcome Dr. Anil Earnest to the event. I welcome you, sir.
Thank you. Thank you. And shall I
A small,
start?
no, sir. First, I have to introduce you.
Okay, thank you.
Okay. Dr. Anil Earnest, my fellow colleague here at 4PI, is a PhD holder in seismology from Cochin University of Science and Technology, Kochi, Kerala. He began his career as a research assistant in Geosciences Division at National Center for Earth Sciences Studies in Trivandrum, and then later he joined here as a junior scientist. He mainly works on observational and computational studies that addresses earthquake source kinematics, lithosphere stress, etc. using state-of-the-art open source tools. His main interests are in megathrust earthquakes, ocean floor deformation, slab earthquakes, stable continental region earthquakes. Welcome you once again, sir. Now you may begin your webinar, sir.
Yeah, thank you. Thank you. Thank you for the nice introduction. Meanwhile, I will share my presentation now.
Please, sir.
So it's viewable, right?
Yes, sir. It's visible.
So today's talk is about big data seismology. I have phased out into three parts. And today we will be dealing on the basics and fundamentals of the seismological aspects. But overall, the objective of the series is to provide an overview on the emerging field of big data seismology and its importance in geophysics. So this three parts aims at to introduce the concept of big data seismology and its relevance in the field of seismology, then to discuss the volume, velocity, and variety of the seismological data and the challenges involved in managing and processing that data. Another part is to explain the role of the big data technologies in seismology, including cloud-based storage, distributed computing, and high-performance computing. I also plan to look at and highlight the applications of big data seismology, including earthquake detection, seismic imaging, seismic hazard analysis, and early warning systems. Also, we would like to provide case studies of real-world applications of big data seismology and the techniques used to analyze and process the seismic data. And we also outline future directions and opportunities for the research and development in the field of big data seismology. So this will be phased out in three sessions from today and next Thursdays, forthcoming Thursdays. So today's talk outline is on the very absolute fundamentals on for a general audience on what is seismology and to get a feel about how that science evolved over a period of time and then go to and have a feel of what is the definition of big data seismology. Seismology as a science is the scientific discipline by which the vibrational waves that travel through Earth are used to study a range of natural processes, like the structure of the Earth and layering of the subsurface. Subsurface means what and all beneath the Earth's surface, to the dynamics of earthquake rupture. Earthquake can be called as a sudden release of stress accumulated along a fault interface by movement of the lithosphere. Because the stress accumulation it happens over a period of time, this process recurs over space and time. In fact, the below figures actually explain this. And over a period of time, when stress accumulates, it actually leads to a sudden slip in between, which is called as the earthquake. So we can phase out this as interseismic era, where you get a stress accumulation. Then all of a sudden, you get a slip called the earthquake. Then again, a interseismic era, where again the stress accumulation happens. So basically, we can say that there is some cyclicity involved in this process, but it's with the present day know-how, it's actually tough to know the periodicity of this cyclic events. If we look at where and how, especially these earthquakes occur, basically to the first order approximation, we can say that earthquakes occur due to the global plate motions. We already know that Earth is actually covered by lithospheric shells, which do have a relative plate velocity, and they slide past each other. The nature of motion can be something like a spreading out, or they actually slide past each other, called as transform boundary, or colliding each other through a process called convergence. So if you check, most of the earthquakes are actually restricted with plate boundary zones, and among that, 90% of earthquakes are occurring on the convergent plate boundaries, where the plate actually, two plates collide each other. If you check the major 10 most powerful recorded earthquakes, there also the major share of earthquakes are from the convergent plate boundaries. The largest ever known recorded earthquake happened on 1960, 22nd May of 1960 at Chile, with a magnitude of 9.5 earth magnitude. So if you carefully look at whether there are any spatial variations for specific earthquakes, though its magnitude varies, we can see that left-hand side panel shows the slip distribution model for a 2004 MW 9.2 earthquake, which happened at the Sumatra Andaman Plate boundary. Middle panel shows for the earthquake slip distribution for 2011 Tohoku Oki, Japan earthquake, and rightmost panel shows 2010 Chilean earthquake. So basically these figures show where the earthquake nucleated, and over a period of time, within few seconds to minutes time, how it spread all over that nearby vicinity. So if we consider again these earthquakes, whether the energy release, that pattern over a period of time, whether there is any pattern for these earthquakes, we can actually find out from this figure. The red line shows the slip distribution, energy release time, the cumulative time taken for Tohoku Oki earthquake. Same time, black line represents the 2004 Sumatra Andaman earthquake. We can see that though the magnitude of these earthquakes are comparable, or in the nearby range, the time it took for the energy release was very less for the Hokoki Japanese earthquake. And it was almost 600 seconds for the 2004 Sumatra Andaman earthquake. So it plainly shows that there can be differences between the time and energy release for respective earthquakes. Next, we will look at earthquakes and stress field. So figures show how the stress field varies between faulting, and it actually represents the classification of basic types of earthquakes called normal faulting earthquakes, strike slip earthquakes, and thrust faulting earthquakes. The knowledge of the state and state of stress and its variation will provide a better understanding of tectonic processes and nature of the seismogenesis at respective locations. Again, coming back to the global plate velocity motions, we can see that it actually causes high amount of strain accumulation at the plate boundaries. These earthquakes mainly are restricted at the plate boundary zones, and it's built upon the locked fault interface during the interseismic period. In fact, geodetic datasets can be used to constrain the rate of elastic strain built up which invariably represents the seismic moment energy release over the seismic cycle. If we specifically look at our plate region, the Indian lithosphere, we can see that our plate boundary also do have lot of large magnitude or great earthquake occurrences. And it's believed that most of these are still active, and it represents some white patches represents possibly unruptured segments which are bound to rupture, and it's a cause of alarm. So to know all these things better, we will have to have an idea about the history of the science seismology development itself. The present slide actually shows the photograph of Robert Hooke. In his name, the which bears his name, the law of elasticity, and describes the linear variation of tension with extension in an elastic spring. He published this discovery in 1678 and titled As the Extension, So the Force. And today we state this as stress is proportional to strain and forms the first mathematical formulation of seismology. Again in 1755, November 1st, at that time, a great earthquake occurred somewhere near to Lisbon, where city with a population of more than a quarter of a million was one of the largest cities in Europe. About 9:30 a.m., a great earthquake occurred around 200 kilometers southwest beneath the Atlantic Ocean. The city shook for nearly 10 minutes, and approximately 30 minutes later, a tsunami swamped the river there, which runs through the city center. This event was the first event to be scientifically studied. Michael proposed that shaking was caused by wave propagation from a distant source, so that the waves were very similar to those produced in sound in the air. The fundamental studies which happened led to the discovery of P and S waves early in the part of the 19th century. In 1830, Poisson published a paper showing that there were two fundamental elastic waves, P and S waves. Poisson's ratio, which is even used today, widely used in seismology, is a measure of the ratio of S to P wave velocity. Later on, in 1840s, Robert Mallet, not only the inventor of the word seismology, he was considered the first seismologist. Born in Ireland, he was an engineer of considerable skills, and his contribution to seismology marked the birth of the science. He constructed the first comprehensive earthquake catalog, which is seen on the as a map on the right topmost side. And in the late 1840s, used explosions to produce seismic waves. And thus he investigated the idea that seismic waves can travel at different speeds in different rock types. Following this, in the 1857 earthquake, Mallet traveled to Italy and used the orientation of cracks and surface exposures and fallen masonry. He produced a isoseismal map for the event. Isoseismal means the same intensity locations. He used contouring technique, and he came out with a map so that a source zone identification can be done. It's called as isoseismal map in seismology. Then in the year 1825, a man called John Milne, a 25-year-old mining engineer, was invited to become a professor of geology at the Imperial University of Tokyo. John Milne organized a seismic survey in Japan and soon recognized the importance of improving the seismogram. Milne was a great promoter of instituting worldwide seismic network and designed several types of seismometers and made the first accurate global travel time curves. Another important event happened during 1889. During this time, at Potsdam, Germany, they were able to record a deep Japanese earthquake, and this is believed to be, which is believed to be the first teleseismic event recording happened and a seminal contribution for the seismology development. During 1906, at the turn of the century of San Francisco, was a bustling sports city with a population of 4 lakhs. Early on morning of April 18th, a major earthquake occurred on the San Andreas Fault, and the city by the bay was devastated. A nearly 400-kilometer long section of the fault slipped, with offsets as large as 8 meters. Many of the structures in the city were destroyed, but much of the damage was caused by ensuing fires that burned out of control for days. The state of California set up a commission headed by Reed and Gilbert to study the earthquake, and the resulting report laid out the theory called elastic rebound theory, which forms the core of understanding earthquake cycles even today. On September 1st, 1923, Tokyo, one of the deadliest earthquakes of this century, struck the heavily populated Kanto province in Japan. The death toll in Tokyo exceeded 1 lakh, and nearly 2 million people were left homeless. Seismology was a developed science in Japan on those days, and Professor Omori had studied earthquakes in Japan. And in 1922, he concluded that the region around Tokyo was seismically quiet and predicted that an earthquake would strike in the region in the near future. This led to, after the 1923 earthquake, the Imperial Earthquake Investigation Committee was formed and produced 5 volumes of scientific and engineering studies, which dramatically improved the building practices in Japan. During 1930s, another famous seismologist, Watati, noticed that earthquakes within the same epicenter had very different patterns of P and S wave arrival times. He reasoned that this phenomena was due to different focal depth, otherwise depth below the surface to the earth, for the earthquakes. Vadati proved conclusively that these deep focus earthquakes occurred and showed that depths of these events formed an inclined zone beneath Japan, which are recognized as subduction zones. Vadadi's observations had a profound effect on Arthur Holmes, a fellow geologist, who in turn produced the first 2D picture that suggests plate tectonics in 1933, which is seen on the rightmost panel. On the screen, we can see the first well-known woman seismologist, Ing Lengman. She discovered the inner core, a zone of solid material at a depth of 5,150 kilometers in early 1930s. She worked at the Copenhagen Observatory and carefully measured the arrival times of seismic phases from distant earthquakes. From this study, she noted that the only way to explain the core phases was to have a boundary within the core with an increase in velocity, seismic velocity. From this, she hypothesized that the inner core was solid, which was later proved on the basis of free oscillations. During 1935, Charles Richter was amassing a catalog of earthquakes from California region. He wanted to publish the catalog with size of the earthquakes instead of how the intensity varied. So he developed a measure of earthquake size based on two fundamental principles. The level of shaking experienced at a distant site will depend on the size of the earthquake, and level of shaking will decrease the farther the distance traveled by the seismic waves. Richard used these principles to develop a logarithmic scale. Each unit of scale corresponds to a tenfold increase in shaking, which became known as the Richard scale. Although Richard's early work was only applicable to Southern California, it served as a basis for modern magnitude scales and is used even today. On July 16, 1945, the US detonated the first nuclear weapon in central New Mexico. The test, codenamed Trinity, had an explosive yield of approximately 15,000 tons of TNT. The closest seismic station was at Tuscan, and the seismologist Gutenberg used the record to determine the origin time of the explosion. The ability of seismically record this and other explosions gave rise to the field of verification seismology. On May 2nd, 1960, the largest earthquake occurred in the recorded history in southern Chile. This earthquake ruptured a 1,000-kilometer section of the subduction zone where Nazca Plate descends beneath Chile. The event triggered a tsunami that not only devastated the coast of Chile, but killed 61 people in Hilo, far away in the Hawaiian Islands. At Hilo, the tsunami height was measured to be above 10 meters. The Chilean earthquake was the first event to produce free oscillations of the Earth. Free oscillations are vibrations of the entire planet and can be used to detail the structure of the Earth's deep interior. During 1965, Tuso Wilson found that the spatial variation of earthquakes was a fundamental in developing the theory of plate tectonics. Tuso Wilson made a major contribution with the discovery of transform faults, which are shear structures with significant motion that are abruptly terminated by ridges or collision zones. Another deadliest earthquake, which happened in China in the early 20th century, was on July 28, 1976. This caused a death toll on the range of 5 lakhs. The industrial city where the earthquake occurred was totally destroyed when a 150-kilometer section of the strike slip fault, which ran through the city, slipped more than 7 meters. Further developments actually led to global tomography models. For example, the figure shows that using a very large number of earthquakes, it's possible to map changes in seismic velocity throughout the interior of the Earth, known as tomographic slices. These slices can be used to show descending slabs and upwelling of hot material within the deep interior of the Earth. Later on, New Age satellite-based studies started helping in quantifying the deformation due to earthquakes. The sudden slip along a fault during an earthquake can cause permanent deformation on Earth's crust. This deformation can be measured from space by a technique called INSAR, or the Interferometric Synthetic Aperture Radar. By comparing two radar images taken before and after the earthquake, it's possible to measure changes in the ground surface. This technique was used to produce a map, for example, seen in the right, of the crustal deformation following the October 16 Hectormine earthquake happened on 1999. Similar developments led to the something like,
Anil sir,
yeah,
Anil sir,
please.
just repeat the last 10 seconds because of the noise behind. We would have missed it. Just repeat the last 10 seconds of the INSAR portion.
Yeah, I will.
Yeah.
The advent of space-based observational systems started helping quantifying the deformation which happened coseismically. The sudden slip along a fault during an earthquake causes permanent deformation of Earth's crust. This deformation can be measured from space by a technique called INSAR, or Interferometric Synthetic Aperture Radar. But by comparing two radar images taken before and after an earthquake, it's possible to measure changes in the ground surface. This technique was used to produce a map, for example, as shown in the right, of the crustal deformation following the October 16, 1999 Hector Mine earthquake, which was of a magnitude 7.1. Similarly, nowadays we have large real-time network of seismic observatories all over the world. Real-time collection of seismic data nowadays allows for construction of maps depicting shaking intensity within seconds of an earthquake occurrence. These are called as shake maps, and shake maps can highlight areas of expected damage and help provide rapid emergency response, as is shown on the right side of the Hectormine earthquake map. So that actually leads to me to compile some of the spectrum of Earth deformation processes. From the already presented material, we can understand that Earth deformation contains a wide range of time scales from seconds to years, millions of years scale, as well as it do have length scale from millimeters to thousands of kilometers. And these contain various nature of processes like earthquake displacements, post-seismic deformation, even solid earth tides, and tectonic strain, etc. And most of the causative process, primary process which leads to these all deformation is a underlying process called mantle convection. If we compile all these things as a single timeline, the topmost panel shows the worldwide seismograph network, which was initiated somewhere in 1960s. And in the early 1880s, we started observing teleseismic events. And 1900s, we were able to discover the Earth's core. And 1960s, we were able to establish the plate tectonic theory. And by 1980s, we were able to come up with digital seismograph network called Global Seismic Network. And in the late 90s to the early 2000s, we were able to actually come up with something called large wide array of transportable seismic networks and all. This evolution actually led to high resolution images of the crust and mantle for the Earth. And by the end of 2010s, we started considering that the science has evolved to a new domain called big data seismology. So, what is big data seismology? Big data seismology can be defined as a subfield of geophysics that involves the application of big data techniques and technologies to manage, process, and analyze large volumes of seismic data. It encompasses the use of advanced computing and data analysis methods to process the vast amount of seismic data generated by seismometers around the world, with the aim of improving our understanding of earthquake processes, predicting seismic hazards, and developing early warning systems. This field involves the integration of traditional seismological methods with most modern big data technologies such as machine learning, distributed computing, and cloud-based storage to enable rapid and accurate analysis of seismological data. So for today, I am winding up with this, with the planned phase I'm in next talk on the large observational networks all over the world, which actually observes the seismic as well as geodetic deformation happening all over the world, and how high performance computing and cloud computing techniques are used to gain insights from these data sets, such as for going for the advanced computing of seismic wave fields, as well as big data analytics or data processing and measurement needs. Thank you.
Thank you, Anil sir, for this wonderful talk. I'm sure the students will know the history of seismology pretty well by now. It was a very informative talk. We shall wait for next 30 seconds to see if we get any questions on our chat box.
Yeah.
As of now, I don't see any questions on the chat box, Anil sir. Uh, folks, to viewers, if you have any questions, we will provide mail ID in our YouTube login portion, so you can mail your questions to the same login ID. Thank you for joining here today. Once again, thank you, Anil sir. Thank you, Jade ma'am.
Thank you.
Thank you. Namaste. Have a good day.